I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of three problems from group theory from the section Algebra, which have appeared in the CSIR National Eligibility Test held in the month of December 2019. These questions are suitable for all these examinations. Right. This is the question. Bearing the question ID is this big number for 3 marks. And the question is related to S5, the symmetric group on 5 symbols. The given question is, let S5 be the symmetric group on 5 symbols, then which of the following statements is false? We are given 4 options. Option 1, S5 contains a cyclic subgroup of order 6. Option 2, S5 contains a non-abelian subgroup of order 8. Option 3, S5 does not contain a subgroup isomorphic to Z by 2Z cross Z by 2Z. It is same isomorphic to Z2 cross Z2. Option 4, S5 does not contain a subgroup of order 7. Right. Let's now discuss the solution of the problem in detail. We are given S5, the symmetric group on 5 symbols, and required to find the false statement out of the 4 statements given in options. Right. And look at option 3. S5 does not contain a subgroup isomorphic to Z by 2Z cross Z by 2Z. Z by 2Z cross Z by 2Z is isomorphic to Z2 cross Z2, and it is very well known that Z2 cross Z2 is a Kleins 4 group, but that is K4. But the K4 is a subgroup of S4. It is a subgroup of S5. I will show you an example where K4 is isomorphic to a subgroup of S5. So S5 contains a subgroup isomorphic to Z by 2Z cross Z by 2Z. But it is given does not. Therefore, this is the false statement. So option 3, S5 does not contain a subgroup isomorphic to Z by 2Z cross Z by 2Z. Let H be the subgroup containing the elements, identity, fixing all the elements, 1, 2, transposition, 3, 4, the transposition, and the permutation 1, 2 multiplied by 3, 4. And recognize this one as the K4. How? Think now. It is E, A, B, C. See now, A square is equal to B square is equal to C square is identity, and AB is C, BC is A, and CA is B. These are the defining relations for the Kleins 4 group. Therefore, it's isomorphic to K4. Clearly, H is a subgroup of S5 and H is isomorphic to K4. And further, we know that Z by 2Z cross Z by 2Z is also isomorphic to K4. It's a well-known result. And many times we might have worked out this one. Thus, H is the subgroup of S5, what I am showing. H is isomorphic to K4 and K4 is isomorphic to Z by 2Z cross Z by 2Z. So therefore, S5 contains a subgroup isomorphic to Z by 2Z cross Z by 2Z. But in the option, it is given does not contain, therefore option 3 is false and required to find the false statement out of the 4 statements given in the options. So we have found out that one, therefore we got the answer. The answer to this question is option 3, and that is the detailed discussion of the given question. And the question is over. But our people will ask how the remaining options are not true. That I will show you in the next slide. Right. We take option 1. S5 contains a cyclic subgroup of order 6. Right. For this, we give an example. S5 contains. Yeah, we have to show the existence of a cyclic subgroup in S5. So, let H is the cyclic subgroup generated by the permutation 1, 2, 3, the cycle multiplied by 4, 5, the transposition. It is a cyclic subgroup of S5 generated by this permutation, which is the product of 2 cycles. First cycle is 1, 2, 3 of length 3. It is second one is a cycle of length 2, 4, 5. Right. And this 1, 2, 3, 4, 5 is a product of 2 disjoint cycles. So this is the first cycle. This is the second cycle. There is no element common between them. Disjoint cycles of length 3. This is of length 3 and this is of length 2. And it is very well known the order of this permutation, which is the product of 2 disjoint cycles, is given by LCM of the lengths of the cycles, that is 3, 2. LCM of 3, 2 is 6 because the GCD of 3 and 2 is 1. Thus S5 contains a cyclic subgroup of order 6. Right. So therefore, the option 1 is true. But we have to find out the false statement. Option 4 we take, which is easy. That is why we have taken S5 does not contain a subgroup of order 7. Assume is a proof by contradiction. Assume that S5 has a subgroup H of order 7. Recall Lagrange's theorem. So, by Lagrange's theorem, the order of H divides order of S5. That is, order of H is 7. 7 divides 120, which is a contradiction. Therefore, your assumption that S5 has a subgroup H of order 7 is not true. Therefore, S5 does not contain a subgroup of order 7. So, the statement is true. Therefore, option 4 is true. But we have to find the false statement. We move to the next slide for the next option. That is option 2. S5 contains a non-abelian subgroup of order 8. Yes, this is also true. Let H be the subgroup generated by 2 permutations alpha and beta. Alpha is 1, 2, 3, 4, a cycle of length 4, and beta is the transposition 1, 3. Now study the properties. So the idea here is these two will generate a D4, the dihedral group. Right. Now, what are the defining relations? Alpha to the power of 4 is the identity, beta square is equal to identity, and beta alpha beta, that is beta is 1, 3, alpha is 1, 2, 3, 4, beta is 1, 3. Multiply 1, 3. If you multiply 1, 2, 3 and 1, 3, you will get the permutation 1, 4, 2, 3. Now again multiply. If you multiply, you will get 1, 4, 3, 2. 1, 4, 3, 2 is the inverse of alpha. Inverse of alpha. So thus we got alpha power 4 is E identity, beta square is identity, beta alpha beta is alpha inverse, and this is precisely the defining relations for D4. So thus H is isomorphic to D4. What is D4? D4 is a non-abelian group of order 8. So now order of H is 8 and H is non-abelian. Since order of D4 is 8 and D4 is non-abelian. D4 is non-abelian. Thus S5 contains a non-abelian subgroup of order 8, which is true. Thus option 2 is also true. Now, identifying two permutations of this type which have these properties is difficult. Some of our students said, therefore I will give you an alternate method. And the alternate method is it is well known that D4 is a non-abelian group of order 8. You can see in our textbook of Algebra by Gallian, this is a direct result. D4 is a non-abelian group of order 8. And it is known D4 is a subgroup of S4. This is there in a Gallian book. D4 is a non-abelian group of order 8 is very well known. And this is D4 is a subgroup of S4 is there in a Gallian book. And further, S4 is a subgroup of S5. Yes. Take S5 and fix any one symbol, then you will get S4, which is S4 is a subgroup of S5. So that's what we have proved. S5 contains a non-abelian subgroup D4 of order 8. It's the same result. And thus the option 2 is true. S5 contains a non-abelian subgroup of order 8, and we have to find the false statement. We have already found the false statement, that is option 3. The answer to this question is option 3, and that is the detailed discussion of the solution of this problem. Right. Let's move to the next question. Right. This is the question with question ID, this one, for 3 marks. And this question is related to a group of any group of order p to the power of n. The given question is, let G be a group of order p to the power of n. P is a prime number and n is a natural number greater than 1. Then which of the following is true? Options. We are given 4 options. Option 1, center of G has at least 2 elements. Option 2, G is always an abelian group. Option 3, G has exactly 2 normal subgroups. Exactly 2 normal subgroups means G is simple. Right. Option 4, if H is any other group of order p to the power of n, then G is isomorphic to H. Let's now discuss the solution of the problem in detail. We have G, a group of order p to the power of n, where p is a prime number and n is a natural number greater than 1. Right. Look at all these 4 statements. And we have to find out a true statement, only one statement. And look at option 1. Center of G has at least 2 elements. If you have a G of order p to the power of n, where p is a prime number and n greater than 1, it is very well known. The center ZG is not trivial. That means order of ZG is greater than 1. It's a very well known result. That means order of ZG will contain at least, order of ZG is at least 2. That is, center of G has at least 2 elements. So that is well known result is there. Therefore, I will tick 1. So question is over. Option 1, center of G has at least 2 elements. Given G is a group of order p to the power of n, where p is a prime number and n is a natural number greater than 1. Now recall this result. If p is a prime number, G is a group of order p to the power of n for some n greater than or equal to 1, then G has a non-trivial center that is order of Zg greater than 1. Therefore, order of Zg is greater than or equal to 2. That means order of Zg is at least 2. That is Zg has at least two elements. That is, center of G has at least 2 elements. So, order of Zg greater than 1, this implies center of G has at least 2 elements. So, the option 1 is true. Therefore, the answer to this question is option 1. And that is the detailed discussion of this problem. Right. Let's move to the next slide. And I will show you options 2, 3, 4 are not true. Right. Option 2. G is always an abelian group. That means G is a group of order p to the power of n, where p is a prime number, n is a natural number greater than 1. Greater than 1. It is wrongly written. N greater than 1. Right. G is always an abelian group. Not necessarily. If you take G is a group of order 8. G is a group of order 8. And that is not abelian. If I can show, then this is false. So consider D4. D4 is order 8. Order 8 is 2 cube. It is a non-abelian group. Non-abelian group. So when order of G is p to the power of n, p is a prime number, n greater than 1, it is not necessarily it is an abelian group. Let G be the dihedral group D4. It is well known that D4 is a non-abelian and its order is 8, that is 2 cube. So that means G is an abelian group in this case. Therefore, G is always an abelian group is not true. So option 2 is not true. Option 3. G has exactly 2 normal subgroups. Only two normal subgroups. So let's see. Let us now consider G is equal to Z8, the cyclic group of order 2 cube. And the number of subgroups are given by tau of 8. How to calculate tau of 8? Tau of 8 is tau of 2 cube. And that is 3 plus 1, that is 4 subgroups are there. So this Z8, so in this case of Z8, it has 4 subgroups. And Z8 is an abelian group. And every subgroup of an abelian group is normal. Therefore, Z8 has 4 normal subgroups. Since G is Z8 is abelian, then every subgroup is normal. Therefore, G is Z8 has 4 normal subgroups. But it said when G is a group of order p to the power of n, where p is a prime number n greater than 1, then G always has 2 normal subgroups, not necessarily. In this case, it has 4 normal subgroups. Therefore, option 3 is not true. Let's move to option 4. If H is any other group of order p to the power of n, then G is isomorphic to H. So consider 2 groups of order p to the power of n and show that they are not isomorphic. They are not isomorphic. So the best example will be Z8 is a order 8 and D4 is of order 8, and are they isomorphic? D4 is non-abelian and Z8 is abelian. Therefore, they don't have any isomorphism between them. Therefore, they are not isomorphic. So let G is Z8 and H is D4. Both are of order 2 cube and they are not isomorphic. Why? Because Z8 is abelian and D4 is non-abelian. Thus, if you take any 2 groups of order p to the power of n, then they need not necessarily be isomorphic. So option 4 is not true. So the only true option which is option 1. Therefore, the answer to this question is option 1, and that is the detailed discussion of the solution of this problem. Right. Let's move to the next question. This is the question that has appeared with this question ID, and it is related to irreducible permutations. And what is an irreducible permutation? We normally do not see this definition of irreducible permutation on permutation groups anywhere in the textbooks. But this is here is a definition given to you. A permutation sigma of bracket n always denotes the set consisting of 1 to n, is called irreducible if the restriction of sigma to bracket k means the set consisting of 1, 2, 3 up to k, is not a permutation of bracket k for any 1 less than or equal to k less than n. Let a suffix n be the number of irreducible permutations of bracket n, then a1 is equal to 1, a2 is 1 and a3 is 3. These are the verified things what he has given. Then the value of a4 is, what is a4? a4 is the number of irreducible permutations on bracket 4, that is 1, 2, 3, 4. How many? That is the question. That is the question. So when a sigma on bracket n, that is 1 to up to n, is called irreducible, it is irreducible if the restriction sigma to bracket k is not a permutation of bracket k for any 1 less than or equal to k less than n. So that means for bracket 1 it should not be, for bracket 2, bracket 1, 2 it should not be, bracket 1, 2, 3 up to n minus 1 it should not be a permutation. Then it is called irreducible. And these are the results given to you. And now let's now discuss the solution of the problem in detail. We have to find A4, the number of irreducible permutations on bracket 4. Bracket 4 is the set consisting of 1, 2, 3, 4. Now we have to find out the permutations on bracket 4, that is 1, 2, 3. That means they are the permutations of S4. So that means all elements of S4 are the permutations of 1, 2, 3, 4. Let us list them one after the other. So S4 is of order factorial 4, and that is 24 permutations are there. These are the 24 permutations that we have written, right? The last one is cycles of length 4. Right. These are the 24 permutations. Now sigma belongs to S4 is irreducible. Definition we are recalling once again. If sigma restricted to bracket k is not a permutation on bracket k for any 1 less than or equal to k less than or equal to n. I will elaborate this. That is sigma restricted to bracket 1, that is consisting of one element only, and sigma restricted to bracket 2 consisting of elements 1, 2, and sigma restricted to bracket 3, that bracket is 1, 2, 3, are not permutations of bracket 1, bracket 2, bracket 3 respectively. If they are not permutations, I mean sigma restricted to 1, sigma restricted to bracket 2, sigma restricted to bracket 3 are not permutations on sigma 1, sigma 2, sigma 3, bracket 1, bracket 2, bracket 3, then they are the irreducible permutations. Right. Now let us illustrate, make an illustration here, few examples. Now if sigma restricted to 1, that means sigma restricted to bracket 1, its action on 1 is 1, then sigma is reducible. Why? Why? That sigma on bracket 1 is a permutation, because 1 is going to 1. When it is a permutation restricted to bracket 1, it is not it is reducible. It is not irreducible, it is reducible. Right. So this is the table, ready-made table I have made for you. First case, E. What are those permutations? When restricted to 1, sends 1 to 1, E. E fixes every one. 1, fix 1, fix 2, fix 3, so on and so forth. Sigma restricted to 1 is 1. That means it is a permutation on bracket 1 to bracket 1. So it is reducible. Right. Permutations flipping 1 and 2. That means mapping 1 to 2, 2 to 1. That means all transpositions containing 1 and 2. For example, transposition 1, 2. It should contain 1 and 2 is reducible. How? 1, 2, transposition. Sigma restricted to bracket 1, so 1 maps to 2. Sigma restricted to bracket 2 of 1 is 2. Sigma restricted to bracket 2 takes 2 to 1. 1 to 2, 2 to 1. So it is the bracket 2 is mapped to bracket 2. That is set constraint 1, 2 is mapped to set constraint 1, 2. It's a permutation on 1, 2. It is reducible. And the third variety is permutations fixing 4 are reducible. So, for example, 1, 3. It is fixing 2 and as well as 4. But our concern is fixing 4. So, it fixes 4. So, now let us take 1, 3. Sigma restricted to bracket 1 sends 1 to 3. Right. Sigma restricted to bracket 2 sends 1 to 3. Sigma restricted to bracket 2 sends 2 to 2. Because 2 is fixed here. Sigma restricted to bracket 3 of 1 is 3. Sigma restricted to bracket 3 on 2 is 2. Sigma restricted to bracket 3 on 3 goes back to 1. So that is here the sigma 3 at the bracket 3 is bracket 3 maps to bracket 3. That means it is a permutation restricted to bracket 3. So it is reducible. Now take the example of this one, 1, 4. 1, 4. 1, 4 doesn't belong to any one of these categories. It is not fixing 1, it is not flipping 1, 2, it is not fixing 4. So what this will be? What this will be? And our claim is it is irreducible. Sigma restricted to bracket 1 of 1, it is 4. Sigma restricted to bracket 2 of 1 is 4. Sigma restricted to bracket 2 of 2 is 2 because it fixes 2. Sigma restricted to bracket 3, 1 is 4. Sigma restricted to bracket 3 on 2 is 2. Sigma restricted to bracket 3 on 3 is 3. So now that means sigma restricted to bracket 1 is not a permutation on bracket 1, and sigma restricted to bracket 2 is not a permutation on bracket 2. Sigma restricted to bracket 3 is not a permutation on bracket 3. Fails in all cases, then it is said to be irreducible. It is said to be irreducible. So these are the examples that will motivate you, and I will discuss for each one of these 24 permutations. Right. These are the 24 permutations which I have written. And now, if sigma restricted to bracket 1 sends 1 to 1, then sigma is reducible. What are all those which will send 1 to 1? E fixes 1. 2, 3 fixes 1, 2, 4 fixes 1, 3, 4 fixes 1, 2, 3, 4 fixes 1, 2, 4, 3 fixes 1. These are reducible. Cancel off all of them. E, 2, 3, 2, 4, 3, 4, 2, 3, 4, 2, 4, 3. Right. What is the second category? Permutations flipping 1 and 2 are reducible. After doing this one, look at them. And what are those permutations which flip 1 and 2? So maps 1 to 2, 2 to 1. So 1, 2 transposition, yes. And the permutation 1, 2, 3, 4. They are reducible. Of course. Now 1, 2, 1, 2, 3, 4. Right. Now the third category is permutations fixing 4 are reducible. After this, 1, 3 fixes 4. 1, 2, 3 fixes 4. 1, 3 fixes 4. So they are reducible. 1, 3, 1, 2, 3, 1, 3, 2. Right. The remaining are all irreducible. Now the number of permutations which are reducible are, here it is 6, here it is 2, here it is 3, and the sum is 11. So A4, the number of irreducible permutations of bracket 4, that is set consisting of 1, 2, 3, 4, is the total number of elements 24 minus reducible ones 11, and that is 13. So 13 is our answer. So let's look at our options. Our 13 appears against option 2. Therefore, the answer to this question is option 2. And that is the detailed discussion of the solution of this problem. And except this third problem, the last problem in this video, the remaining 2 problems are dead easy problems. This question is also easy, provided you understand the definition what he has given to you. Right. This is a kind of a counting that I have made, and it is an indirect counting. Agreed. I am sure that you have understood the solutions of these 3 problems. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Right. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.